Uh, Our today's talk will be about operation of RAS, pumps, and aeration. So we will again have a little bit of a quite technical part of the webinar, and then some more operational informations that will be mainly given by our co-host today from the National Aquaculture Research Center in Jordan, Dr. Ahmad Al Khraisat. What we will look into today is, again, like I promised last time, that we will have a closer look once again into the determination of the required flow rates in the fish tank that we would need to maintain the right water quality. And we will link that to an example of an existing system to make probably more clear how this has to be done. And we will refer to this example quite a few times during this webinar to make things a little bit easier to understand and a little bit more based on practice. We will talk about suitable pumps for the aquaculture and the hydroponics in our systems. So water pumps in this regard, and also to suitable aeration. We won't look too much into oxygenation in this case, because we'll think about smaller and simpler RAS systems that can get away with aeration in general, because they have not that high fish densities in the fish tank. And then in our last chapter, we will have some insights from Dr. Khraisat, who will talk about maintenance and troubleshooting in their systems at NARC, and give us some practical insights from his point of view and his experiences. So let's start again with the part about flow rates and water quality. I just show this small picture again to remind you of what we are aiming for. We always try to keep every water parameter that is important for our fishes in this optimal range where they grow the best, and the general, I will get this away. Their livelihood will be the best too, and we tried really to keep it into the optimal range and take actions as soon as we leave that, so that we only occasionally get into the tolerance range. I already talked last time also about the different control strategies for water quality, and we will focus on the last one, the recirculating system with filtration, where the filtration has to be so good that with a given flow rate, we can maintain water quality in these wanted parameters, while we still can recirculate up to 99% of our water. So we are saving really much of water. Here I already put in some figures from the example we will talk about today. If we would control our example system with a flow-through control strategy, we would need about 5,500 liters a day. And when we include filter system and can recirculate the major part of our water, we only would need about 90 liters of fresh water per day. This is a huge difference. So it's worth probably to put the effort into building some filter systems to save water. Here are again the treatment devices that will make up our filter system. After the fish tank, in general, we tend to have directly the solid removal unit, because solids contain a lot of organic matter, and this has harmful consequences for later treatment devices, like, for example, the biological filtration. They also generate a lot of oxygen need. So it's best if we remove as quickly as we can the major part of the solids from our system. Then we have this biological filtration that transforms ammonia to a nitrate in the end. And usually we try to have somewhere in the system one pump that pumps the water up one time, and then the whole rest of the system is running by gravity. And oftentimes a possible place where we can put the pump would be behind the biological filtration, or in a sump tank that is directly behind the biological filtration, or in some systems, the biological filter unit itself is also the sump tank, and we have the pump connected to this device. And only after the pump, we will have disinfection if we need it, degassing and oxygenation if we need this free. We will not talk about these today because we depart from the idea that we will have a simple system with a low fish density that has not to make use of these devices, but only aerates the biological filter and also directly the fish into the fish tank so that they have enough oxygen only with aeration. This will be the example system we will talk about in our practical examples. It's a very simple aquaculture RAS system with a sump tank here that is buried a little bit into the floor, a simple fish tank made up of an IBC tank, and a filter section that has two different solid removal units, a radial upflow filter and a sand filter. We don't have a biological filter in this system. It could be placed into the sump tank where we could put just some biomedia where bacteria could live, and then we would have a biological filter there. But this aquaculture unit is usually linked to a hydroponics unit to make up an aquaponics system. And then we use media beds, growing beds, as a biological filter in the system so that we don't have it in the RAS. The system is designed to allow a carrying capacity of 25 kilograms of fish, either tilapia or catfish. But we also had some partners who did stress tests with this system up to 80 kilograms of catfish per cubic meter of water with adjusted flow rates, obviously. But this showed that the system can handle quite more than 25 kilograms, but we will stick to that with all our examples because it's a way that we usually want to be operated, this system. If you look at our example that we will use today, or the two fish species that we usually rear into this example system, we have tilapia or African catfish, and here we see the some selected water quality parameters that we define for these different fish species. We see that they differ a little bit. Main difference is that catfish is a little bit more robust and can handle a higher total ammonia nitrogen, and also a little bit less oxygen. I tend to give the dissolved oxygen amount as partial gas pressure, because this is what is important for the fish. If we look at the exchange of oxygen while they breathe through their gills, and it's a possibility to give the dissolved oxygen in a measurement that adapts by itself to water temperature and pressure. That's why I like it. So where we always have to start from if we want to define the water flow rates is a production rate of a certain substance that we want to remove from our tank, because when we produce more of a substance, we will need a higher flow rate to get it out of the tank in a given time and to maintain the water quality that we are looking for. For that, we need the peak feeding rate. From that, we can calculate the excretion per day of this given substance. That's why always I have this S. This is for substance. And from the daily production rate, we can transform the grams per day into milligrams per second by dividing by 86.4. And that's some point where I usually depart from this mean production rate. But we have to take into account for every substance that we produce that it's not really the same rate of production over the day. But after the first feeding, the metabolism of the fish starts to get working, and thus we have usually a production peak for every substance that is a little bit later into the day, like about 5 or 6 hours. And for substances that are exchanged via the gill, like for example ammonia, the peak will usually be twice the amount of the mean rate. And for substances evacuated by the intestines, it will be about 4 times as high. If you're looking at the African catfish and we are thinking about how we tend to, or we want to control these different parameters in our RAS system, we have to decide, is a water parameter linked to the flow rate through the tank or is it not? So if you look at the dissolved oxygen that we want for the African catfish and we want to aerate inside of the fish tank, this is not linked to the flow rate. This would be completely different if we oxygenate the water, because this is usually done with a separate device outside of the fish tank. And then the rate of oxygen that flows into the fish tank depends on the flow rate that comes from the oxygenator to the fish tank. So this no here really depends on the way that we provide oxygen to the fish tank. In our case, it's aeration, so it's not linked to flow rate. But the temperature in general is not really linked to flow rate. Somehow, probably if we have to heat or cool the water, obviously it will get a little link if we don't have to take care of the temperature actively, because it's always in a range in the environment where our RAS is situated. That is good for the fish. We don't have to do anything, so it's not linked to the flow rate. Total ammonia nitrogen is linked to the flow rate because it is produced by the fish inside of the fish tank, and we have to dilute this with clean water that flows through the fish tank and comes from our filter section. So here it's a clear yes. The pH is not really linked to the flow rate because we don't regulate it with the flow, but actively if we need to interfere by giving some chemicals or whatever that buffer the solution or correct the pH. And again, the total suspended solids are again linked to the flow rate because the fish produces inside of the fish tank. We want to get it out and have to regulate this by a flow that has a correspondent flow rate and comes from our filter section again. So we have two main parameters that are in our example linked to the flow rate. These are total ammonia nitrogen and total suspended solids. But how can we calculate the flow rate? We have to calculate, we do this with a mass balance. So we look at what is produced inside of the tank, what comes inside of the tank of a given substance by the flow. This is what is here in the first calculation. We have this production rate, the peak production rate, because we have to design our system and the flow rates for the worst case. So this is the peak production rate. And what comes into the tank with the flow and the concentration of the substance in the flow that comes into the fish tank. And then we have the removal rate, that is just the flow out of the fish tank multiplied by the concentration of the substance in our fish tank. And these two terms have to be equal. That's what I have here in the mass balance at steady state. So what comes in is equal to what goes out. And usually what we can also state is that the flow rate that comes into the tank is exactly the same what goes out, because if inflow would be larger than outflow, our fish tank would overflow. And if the outflow would be larger than the inflow, then we would empty our fish tank. So these two always are the same. And that's what I already corrected inside of this calculation. And then we have to take into account the efficiency of our treatment device. So how much of the substance that we are looking at is removed by our filter section. And if we look at that, we know that the inflow into our fish tank, as it is a recirculating system, will be the outflow multiplied by 1 minus the treatment efficiency of our device. So what is left after the water got through the filtering device. And if we put all this together, we can solve for the flow rate. And then we get that the flow rate has to be the peak production rate divided by the efficiency of our treatment device multiplied by the maximum allowed concentration that we defined in our water quality parameters earlier. Let's look at an example for the ammonia nitrogen. We have a peak stocking rate of these 25 kilograms per cubic meter. That is the carrying capacity we are planning for in our example system. As it has not really 1 cubic meter of water in the fish tank, the amount of fish is a little bit lower. We have a peak feeding rate of 1.3% per day, resulting in a peak feeding rate of about 300 grams per day. And then we can calculate how much nitrogen will be in the fish feed, how much of this nitrogen will be kept by the fish by his metabolism. This is usually 27.5 grams per kilogram fish. And by subtracting the amount of nitrogen in our fish feed, what depends from the crude protein content, minus the amount of nitrogen that is retained by the fish, we get what is excreted. And if we multiply the excretion rate, that is based on the amount of feed. So in our case, 39 grams nitrogen per kilogram feed, with the feeding rate of 288 grams per day, we get 0.13 milligrams of nitrogen that is produced per second. That would be our production rate for nitrogen. And we can do quite the same for the dissolved solids. Here also we have to take the peak feeding rate that we have, and we know that we have about 225 grams of total soluble solids per kilogram of feed. And thus we can also calculate a rate per second for the production of the soluble solids. And then we have to take into account that these were the mean rates that I just calculated. So we have to multiply by 2 for the ton and by 4 for TSS to get the peak production rates. Then we have these desired water quality parameters, the CS max, that we defined earlier in our water quality parameter sheet. And we have filter efficiencies that for small scale systems are usually about 40% if you do it right for ton and 80% for TSS. And we can calculate based on this formula that I gave you earlier here, this one, Q equals production rate peak divided by treatment efficiency multiplied by CS max. go back here. Peak production rate divided by filter efficiency multiplied by desired water quality, and this equals, for the ton, a design flow rate of 0.22 liters per second, and for the TSS removal, we get, here's the equation 2, 0.05 liters per second. And our design flow rate we have to use in our system will always be the largest of the flow rates that we calculated. So in our case, we have to have a flow rate of 0.22 liters per second, or about 13 liters per minute in our system. So this flow rate has to be delivered by our pump and also every other flow that is needed by our system. We keep that in mind and come now to the discussion of different pumps. Key properties of pumps are flow rate, hydraulic pressure, electric power, efficiency, and tolerance toward solids. The flow rate we need depends on the desired water quality in the fish tanks. That's what we just calculated. And for example, other needs for flow rates inside of our system. In case of our aquaponic systems, this could, for example, be cycle time in media beds or flow rates through a deep water culture or whatever that is added to the flow rate that we need inside of our fish tank. The hydraulic pressure that the pump needs to deliver has mainly two parts. One is the hydrostatic pressure. This is the difference in water level between the lowest point where our pump will be and the highest point where the water will be pumped up. And the hydrodynamic pressure is made up by, for example, friction losses inside of our piping system. Then electric power is just the power that is given inside of the data sheet of a pump, and that defines mainly the electricity consumption of a pump. And there we should always aim to have the lowest electricity consumption possible. And the efficiency of a pump is defined by two ways potentially. One would be to add up the hydraulic efficiency, the electric efficiency, and the mechanical efficiency of our pump. But these three parts are oftentimes not easy to measure or to define. So what we usually do is that we look at the hydraulic power of our pump. So the amount of power that is actually transferred to the water compared to the electric power. And if we divide these two, we get the efficiency of the pump too. We will look at this in our example later too. And then one last point that is important, as I already said, is the tolerance toward solids. That is the size of particles that the pump will be able to transport. This is usually not unimportant because we will have some solids in our fish water, but as a pump is best placed behind the solid removal filter, it usually don't have to transport very large particles. So this is not as important as if you would put, for example, the pump inside of the fish tank. It would have to be much better with regards to the tolerance towards solids. And that's why we usually don't do that. Yeah? Usually we let the water run by gravity to the solids filtration, to the biofilter, and only place the pump behind that. How do we know this or what characteristics a given pump has? Usually we find that in the data sheets, so we can look up everything that we would like to know, like electric power of a pump. And there it's always also given a maximum headroom in general and also a maximum flow rate. And what is very important to understand is that a pump will never reach both maxima at the same time. So we will never have 22 kilopascal at 58 liters per minute for a pump. The reality is usually at probably half of both values. So this pump here would deliver about 30 liters per minute at 11 kilopascal. And what is happening in reality between these maxima that are given in the data sheet of a pump, the one maxima is the maximum hydraulic pressure that in our example was 22 kilopascal. And if we want to deliver this pressure with a pump, it will have a flow rate of 0. And the other extreme maximum flow rate, this was given as 58 liters per minute. We would have a pump pressure of 0. So this would just be water running, pumped out directly from the nozzle of the pump. And what we have in our system usually is something that is on this blue line, that is a pump characteristics line. So we probably would have 25 liters per minute at about 14 kilopascal. Yeah, everything that is on this blue line can be delivered by the pump. And if we look at the hydraulic power, that is the multiplication of these two values, so the flow rate and the hydraulic pressure, we see that we have some graph like this red one here, where if we go to the extremes, we will always multiply one value that is 0, like flow rate here at the maximum pressure 0, or pressure 0 at the maximum flow rate. And in between, we have some kind of, well, let's call it parabolic graph. And it has some maximum at about half of the two values. And this is where our pump has the best efficiency, because it transfers the maximum hydraulic power to the water. So we have the most water pumped per electricity unit that we put into our system. So this would be the perfect point where we would want to use this pump. And this would be at about 32 liters per minute and 13 or 12 kilopascal. And we should choose pumps according to this aim, or we should aim for using pumps that have that work as close as possible to this peak in maximum hydraulic power. In our case, at this point here, we have a hydraulic power of 6.25, and the pump had an electric power of 30 watts. So the efficiency would be 0.21. That's not really good, but it's not that bad either for small pumps. And as well as our pump has this characteristic here where the flow rate changes with hydraulic pressure, we can also define such a curve for our piping system. And this is also quite understandable. If we have no flow inside of our piping system, we will also have no resistance, no friction, no pressure loss. And the more water we try to pump through our pipes, the higher the friction loss and the hydraulic pressure we lose will get. And at some point, these two graphs of the hydraulic pressure inside of our piping system and the pump characteristics intersect. And this will be exactly the operating pump that we will have for our pump in our system. So let's look at the example again. We already calculated that we would need a flow rate of 0.22 liters per second in our fish tank. But as I already said, in our training system in Cities Food that we also use as a basic demonstrator in FrontAg Nexus, we will add some hydroponic units to make up a aquaponic system. And we would need another 0.1 liter per second for the deep water culture that we would want to include. We would have 2 media beds that would also need 0.1 liters per second each, adding up to 0.2 liters per second, and some nutrient film technique pipes that also would need some flow rate, adding up to a flow rate of about 0.67 liters per second or 40 liters per minute. And we planned our training system first with a D25 millimeters training system that is equivalent to 3/4 inch, and calculated the hydraulic pressure for that. That would be 11 kilopascal for the friction loss inside of our piping system, and another 16 kilopascal for the hydraulic pressure, because we will have, if the sump tank gets really empty, a height difference between our sump tank and the fish tank of about 1.6 meters, adding up to 27 kilopascals. And if you look at some pumps that we had in mind that we could probably use for our system, we found out that from the pumps with the different characteristics that we see here in our example, only one is above the calculated operating point. So only one of the pumps would be suitable. Only a quite large pump, the CTP 7000. And this pump uses 50 watts, what we thought is for our small training systems a little bit too much. That's why we reconsidered the diameter of our piping system and tried the same for a 1-inch piping system instead of 3/4 inch. And then we recalculated the pressure loss inside of the system, and it got down by 7 kilopascals to about 4 kilopascals, adding with the 16 kilopascals of hydrostatic pressure to only 20 kilopascals in this modified system. And now we see that our operating point got quite lower, and we can now almost use all the pumps that we had in mind to operate our system. And we could, for example, use the CTP 4800, the green line here. And this pump would use only 30 watts. And compared to the first pump that we have to choose with 50 watts, this is almost half of what we had before. So we see that considering pipe diameters and so can be very important if we want to have a system that has the as few energy demand as possible. Yes, and that's what I already said regarding the economic efficiency. It's quite important to have a look at the operational costs, and if we have less energy use, then we will obviously have also less operational costs in this regard. And the CTP 5000 in our example that we could also use to run our system has a electrical power of 30 watts, and the hydraulic power at our operating point would be 13.3 watts. So the efficiency would be 0.44, what is quite good for such small pumps. Okay. Coming to the next point that we will look at today is suitable aeration. We have not really talked about different methods of aeration before. That's why we do it today, because it's a very important aspect of operating a RAS system. To define how much aeration we would need inside our fish tank, we have to do something similar to the production of substances that we did before for the calculation of the water recirculating pump. We will have to calculate the peak oxygen demand. And this is also done by calculating departing from the amount of feed that we give to our fish. So we will have the same as before, peak feeding rate, feed-related oxygen rate that we would need to provide to the fish. Then we can calculate a daily oxygen demand, from that mean oxygen demand, and then again, with respect to the metabolism and the changes over the day, a peak oxygen demand that we will design our system for. And to transfer this peak oxygen demand into an aeration flow rate, we have to take into account the efficiency that we can produce to dissolve oxygen from air that we pump through the water into the water body. And this usually happens between the surface or at the surface between the air bubble that flow through the fish tank and the water surrounding the air bubble. And that's why it is important how deep our air diffuser is submerged into the fish tank, because if it is deeper, we have a higher pressure that aids, that helps to dissolve or to transfer oxygen from the air bubble into the water, and also a longer way for the bubble up through the water. So the contact time will be longer, and this also helps to transfer oxygen from the air bubble inside the water. And the second parameter that is important for defining the absorption efficiency from oxygen from the air into the water is the concentration of oxygen already present in the water. And then we can look up the absorption efficiency with some graphs like the one that I show here. If we know our water should have dissolved oxygen content of 50% for the well-being of our fish, we will look up at this graph, the red one here, for example. Our diffuser has a depth of about 1 meter. Then we would have an absorption efficiency of only 1.8%. So only 1.8% of the oxygen in the air will get into the water. That's not very much, but that's why aeration is so inefficient. And that's why with larger fish densities, we will use other means to transfer oxygen into the fish water, like oxygenation in a separate device outside of the fish tank. So doing a quick example, we will calculate again for African catfish. We gave in our optimal parameters table the dissolved oxygen partial gas pressure of 8 kilopascal. We know that our optimal temperature for the catfish will be 26 degrees. And this makes the oxygen concentration that we are aiming for, 8 kilopascal at 26 degrees, about 3.6 milligrams per liter. And this corresponds to a saturation of 40%. And at a saturation, at a diffuser depth of about 80 centimeters, because our IBC tank is quite shallow, and a dissolved oxygen amount of 40%, we will have an absorption efficiency of 1.8%. And this we can use to calculate our final airflow rate that we need. This is again the calculations that I showed earlier. We depart from our peak feeding rate. We know that we would need about 350 grams of oxygen per kilogram of feed that we give to the fish inside of our fish tank to provide enough oxygen to our fish. This would be what they usually consume per day. So this would be 100 grams oxygen per day. If we transform that again into a mean oxygen demand by dividing by 86.4, we get 1.16 milligrams per second. If we take into account the peak oxygen demand, that is about 1.25 times higher than the mean, we will need 1.45 milligrams per second transferred to the water. And if we now take into account the weight fraction of oxygen in air and our efficiency of absorption, like 1.8%. We get a flow rate that we need inside of our fish tank of 17.4 liters per minute of air. So we have to pick an air pump that can deliver this amount of air at the depth of our diffuser through a corresponding piping system. Let's have a quick look at the types of diffusers that we could use. This are mainly air stones, membrane disc diffusers, and aerator hoses. These have a little bit different characteristics. The bubble size is a little bit different. Membrane disc diffusers, for example, have very fine bubble sizes. Aerator hoses have rather coarse bubbles. And finer bubbles are usually beneficial to the transfer efficiency. So what we just calculated was probably more for coarser bubbles or medium-sized bubbles. So we could probably have better absorption efficiency if we use something like a membrane diffuser. So we are on the safe side if we calculate with the flow rate that we just calculated. And that's what I also noted here. The oxygen transfer rates are probably moderate for air stones, much better for membrane disc diffusers, and also moderate only for aerator hoses. But also the costs, so the investments are different. Air stones are really low-cost devices, while membrane disc diffusers are more on the higher cost side. But they have also a better durability than, for example, air stones. We would have to exchange the air stones more often than the membrane diffusers. If you would now want to choose the right air pump, we would have to look a little bit at the same characteristics as for a water pump. We would have to look at the flow rate that depends on the oxygen demand of the fish and also the oxygen demand in our biofilter, if we have one. And that would also have to be aerated probably. And also aeration that we would probably need in our hydroponics if we have an aquaponic system. Like in the deep water culture, some deep water culture designs need also aeration. And the pressure loss, or the pressure that our air pump has to deliver, has 3 parts. Also the hydrostatic pressure, like a water pump, only that here the hydrostatic pressure is defined by the submergence depth of the diffuser. So the water column that is above the diffuser would be defining our hydrostatic pressure. Then we have, again, friction losses inside of our piping systems. And in addition, we have the diffuser resistance that also adds to the air pressure that has to be delivered. And then again, playing an important role, the electric consumption of our pump that we should never forget. Very important, we see here friction loss is an important pressure loss, source of pressure loss for our air pump. And oftentimes, people tend to connect air stones in simple aquatic systems with just 4mm hoses, these transparent small hoses that you all know that are really easy to use, but 4mm hoses are so small that when we have to deliver a huge amount of air, like 17 liters per minute, these are so small that we will lose a tremendous amount of pump performance. We will come back to this later again. Then here are some examples of pumps that we could use for small-scale aquaculture systems. We could use membrane compressors, piston compressors, and air blowers. The main differences are that air blowers deliver way larger volumes, but at the cost of lower pressure. Obviously, we could also have air blowers that deliver the same pressure than the membrane compressors or piston compressors. This depends always on the size. But then they would also deliver still a much larger volume flow. And that's why for small scale systems, air blowers are sometimes not the best choice because they just deliver too much air that we wouldn't use up. And they have a higher power usage corresponding to the higher flow they deliver. Generally speaking, we can also get much higher pressures with all these devices, but then we would have to buy just larger ones that deliver higher pressure and also higher flow rates normally. These are just examples that are more or less in the range that we would need for our example. And here again, we have something like a characteristic curve for every air pump that we could look up, and also the same properties. And here it's the same as for water pumps. We never will reach maximum pressure and maximum flow rate at the same time. We will be somewhere here at the blue graph of the pump characteristics. And if we add up all the pressures that our pump has to overcome, then we will find out how much air the pump will deliver at this pressure. And some very important point is here, as an example, I gave again the piping system characteristics. So we have a submerged diffuser. This is diffuser resistance. That's why I did not begin with 0 with this piping system characteristics. And at the intersection of the pump characteristics with the piping system characteristics, we will have our operating point. And again, we want to be to have this operating point as close to the maximum pneumatic power in this case, to have the highest possible efficiency. So what performance would we require in our example? In our example, we would have to have these 17.5 liters per minute for our fish tank. And as we are looking at an aquaponic system that needs, in the case of our design, also aeration for the deep water culture, we would need another 11.5 liters per minute for the deep water culture, adding up to 29 liters per minute. And as our diffusers are submerged about 80 centimeters, this results in a hydrostatic pressure loss of 8 kilopascal. The friction loss in our system would be about 1 kilopascal if we use half-inch piping for our aeration system and lead this half-inch piping as close to the air stones as possible, and only connect from this larger distribution pipe to the different air stones with a 6 millimeter hose for as few distance as possible. Yes, and because if you look at the total of 9.5 kilopascal that are required if we design the system in this way, if we would not use a half-inch distribution pipe for our air, but something smaller like 6 millimeter hose for the whole system, or probably even worse, 4 millimeter hoses, we can quickly reach pressure losses only for the piping system of 6 kilopascal or even 35 kilopascal only for the piping system. And that's where we see that it's really important not to use too small pipings for the aeration system, because then we get up to ranges that we don't want to have if we are looking at the at our pump and also at the electric efficiency of our pump. So if we're again looking at a couple of different air pumps that we could probably use, We calculated a value of 10 kilopascals that we would have as pressure loss in our system. And then if we could look here at the different air pumps, we see that the yellow one, the HP20, delivers not enough airflow at this pressure, but the three others would be usable, but all of them deliver a little bit more than we actually need. We need about 30 liters per minute, and the smallest we could use delivers almost 50 liters per minute. That's way too much, but on the other hand, that gives us a little bit of a security or flexibility if we want, for example, introduce some biomedia into our sump tank to use it as a biofilter, an additional one. We would need some additional aeration for the biofilter too, and we would have that with this larger pump. On the other hand, this would mean that this manufacturer probably has not the right pump for us in his product range, because it has some kind of hole here exactly at the range that we need. So probably we should look up a different manufacturer too. We never know. But one thing that is very important is that if we would choose this HP40 and have a larger flow rate that our pump delivers at this pressure loss, we have to make sure that the diffusers that we use in our system are really able to deliver this air volume to our water body, because otherwise we will quickly break the pump, because it will get way more back pressure than it should have if the diffusers for diffusers, usually there's also a air volume per minute given that a diffuser can deliver. So the sum of all our diffusers should have a flow rate or a deliver rate that corresponds to the flow rate of our pump at the given pressure that we calculated. So some last remarks regarding our air pump, how we install it. I already said we would have to use a large distribution pipe and only use the smaller hoses to connect from this distribution pipe to our diffusers. The air pump should always be placed above the water level of the water body that we want to aerate, to prevent water from accidentally running into our pump. The connection from the supply line to the diffusers should be 6 or 9 millimeter hoses. Do not use 4 millimeter hoses. And the compressor constantly generates heat while he compresses air. And that's why it should be well aerated or ventilated and not get too hot. The best temperature for the operating point for our pump with respect to temperature would be between 10 and 30 degrees. Could be a little bit higher, but take care that it doesn't get too hot, because for a membrane pump, for example, this will quickly break the membrane and shorten very much the life cycle of your air pumps. Having said that, we come to the part about operation of RAS in general and also at NARC. I would just run through 3 or 4 remaining slides before I hand over to Dr. Khraisat. Key aspect for successful aquaculture operations. We already had that in a couple of webinars before. Very important is trained personnel, careful observation and documentation of everything that we observe, so that we can have data-driven decision-making, traceability, transparency, and performance monitoring of our system, so that we can improve over time. And also careful observation so that we can early detect problems, optimize our feeding practices, and monitor water parameters. Best way to do that is to have lots of checklists and routines. Here's an example that we also already had in one of our webinars. checklist what has to be done on what day. Not everything has to be done daily. So we can look up what has to be done on a given day. And below we could have a table where we put in who did it, when, and was there something that was noticeable to be documented. And for every single one of these operations in our checklist, we should also have routines, like, for example, standard operating procedures that we can look at if we are not sure on how to do a certain task. We should also have target sheets for everybody to look at if you're not sure about a certain value in our system. What would be the optimal temperature? What would be the maximum nitrate amount in our water body? And also with given actions, what has to be done if we exceed one of these values, whether it be a optimal range that we leave or a tolerance range. And last but not least, we should also document everything that we observe in our system, or what we do to our system. So everything that is added to the system, whether it be chemicals or fish feed or whatever, should be noted in some kind of documentation. Here is an example for the documentation of the fish feeding or what is happening to the fish livestock or the growth rates. But we should have similar sheets also for water quality parameters, for instance, or other stuff, so that we never forget lessons learned and can optimize and know at every given time what has to be done to our system at the last couple of weeks, for example. Yes. Having said that, I would want to hand over to Dr. Khraisat for his presentation. He will just present a little bit an aquaponic system they have at the NARC, National Agricultural Research Center in Jordan. And probably he will focus a little bit on the part on maintenance and troubleshooting, so that we don't have too much of duplicates in our presentations. Dr. Khraisat, should I share your presentation or will you do that?
Yeah, I will share. Good morning.
Okay.
How are you? I will share, inshallah. The host can be displayed. The host.
Michael, I think it's better if you share your host, and then you, Dr. Khraisat, it should work.
Yes, it's set up on everyone.
Okay. Okay, now share.
Yes, we see the
Yes.
It's working.
Yes,
Great.
Working. Okay, nice.
Yeah.
Yes.
Yeah. Good afternoon or good morning, everyone. It is my pleasure to welcome you in all to this training in section, especially focusing in the recirculation of the aquaculture system, especially we're talking about the aquaponics in the Jordan, the experiment in the Jordan, where can when it start, and after that we talking about that in my research. We will talking about the pumps and the operation, how can, and the aeration technique. My name is Dr. Ahmad Al Khraisat, the head of the Fisheries Research Department. I work in the National Agriculture Research Center, which is follow of the Ministry of the Agriculture. We talking about for the aquaponics. Aquaponics it is combines between the fish and the plant together with the growing plant without soils. This is the innovation for these systems to reduce or minimize the waste and efficient for the recycle of the water. And we know that Jordan, one of the country in the world, have the poor water. So we enter in the research center about the technique which is to minimize for this problem. What is the aquaponics cycles? The aquaponics cycles have 3 steps we should know to start to working. If these principles, when understand how can do, that's meaning we can success in the system, and we can putting many things for the efficient these systems. The first one is the water flow. Water flow, that's meaning from the fish tank, which is the carrying of the nutrient to the plant beds. This is nutrients have rich in the waters, help the plant to grow. This is the first principle, which is important, the relationship between the fish and between the plant. The other things we should look about the plant growth. Plant growth, this is the result for the nutrient from the water and remove the excess ammonia. The ammonia, we are know, it is very toxic nutrient. So we working in the system. If you control the ammonia, that's meaning the fish is live and the plant take the ammonia and to convert by the bacteria to other nutrient very safety for between together. This is process cleans of the water and it is suitable for the fish. The other things, the principle is very important. It is the fish waste. Fish waste does mean the pieces from the digestive system, and the other things is from the feed, the byproduct of the feed. Sometimes maybe the labors, it is introduce more the amount of the feed, or something have a problem in the environment, in the water, so the fish no eat the feed, which is the waste. This is after that. This is the piece it uses the problem for the system, which is an increase the ammonia. Where ammonia it is very toxic, maybe have high fertility for the fish. Other things after the 3 principles, the main 3 principles, depending how can using the machines to reduce or to efficient these principle to success this system. The first one, the importance of the water cycle, it's reduced for the water. In the starting, I am talking about the Jordan is the poorest in the world about the water. So we should this is a technique we now enter and encourage the farmers by the government and for the research center to give the result very correct to the farmers to starting for these technique. Other things is minimize the waste production. How can use by the closed loop system, minimize the water waste, reducing the environment impact and promoting responsible resources management. Other things, it is for the improve the water quality. After the filtration from the grow bed, we doing the improve the water quality after the filtration. That's meaning we should putting of the high quality waters for both of the fish and the plant, which is if reverse and effect for the healthy and balance of the ecosystem. About the RAS, the aquaponics can be converted to the RAS systems by using, after that, to using the storage tank, the same with what I doing in this project. After the water, go to the biofilter, and after that, we can see again, excuse me. This is the biofilter. The water go to the biofilter. After that, go the grow bed, and after that, go to by the siphon bed. We're using to storage for these tank, because it is why the fourth tank, because I am using this is for the research. For each replicate have a treatment, so I am using about the fourth tank in this system. And after that, these tank, we have submersibles pumps go to for the fish. We have even 4 bond. Each bond have different density. So every replicate go to tank, and after that return again to the fish tank. The recycled water, this is which is the closed cycle, reduce for the waste of the water, and utilization the optimal.
Something is wrong.
I think his connection bombed out. Maybe we can wait a bit. Michael, do you have something else to add to the presentation, or maybe we can... Aha, he's back. But muted.
Okay.
Yeah.
Done.
But we need the presentation.
No share?
No share.
Okay,
Probably it kicked you out, so it stopped the share.
1 minute.
I lost the connection.
Doctor, I would suggest we have about
Yes.
10 minutes left.
Yes, yes, okay.
Probably that we skip a bit of the system design part and focus for the 10 minutes a bit more on maintenance and troubleshooting in your system, because I think this would be the most beneficial aspects of your presentation.
Okay.
If you agree.
Yes, okay. We can do that. We can continue, because now I will go to the other what you want to ask about that. The maintain of the water quality for optimal fish of the water circulation. The pump, this is the mechanism. The pump will move the water from the fish tank to the grow bed, where nutrient delivery from what I talk from the fish water nutrients and distributed to the plant, and the oxygenation is very important for the water by the aeration and providing oxygen to the fish plant. Pumping, it is very important for the water circulation and for the water movement, which is the very important and efficient in this system. and the filtration for the waste of the removable and the nutrient distribution for the between together between the fish and the plant about that. The pumps we using in the systems is submersible pumps in my systems in the NARC of the research center. We are using the submersible pumps. This is different kind, but we are using the submersible pump. This is very good for us, and because we can control as the automatic and very the famous machines we can using, because I want to very simple machines, which is that's no about that's to doing and to using in this system. And the aeration we are using for this the nano aeration pipe to increase the aerations in the fish pond. The fish pond we are using of the swimming pond. This is the first time we are using, and the nano aeration pipe is the first time, and we see it is very efficient and very good for the in the working, and we give more oxygen in the water when I am increase of the fish density. We are using in the RAS. What is the difference between the aquaponics and the RAS is for the oxygenation. We should the oxygen is very is essential in the fish respirations and the water quality. How can use or how can increase for this oxygenation? It is by can using of them. This by the surface aeration or the deep aeration. We are in this system we using of the deep aeration because the nano pipe it is in the deep, not in the surface. So we using in this system by because using of the nano aeration. The design, it is different between the aquaponics and the RAS, but we can available or can doing something in the system to using as the recycled water, the same what are we doing in the station. We talking about because the irrigation is very important in the aquaponics because many problems in this technique when the farmers in the Jordan using for the aquaponics, he have a problem for the deficiency in the plant nutrients, and he don't know how many density of the fish we can use in the cubic meters. And the irrigation is have a relationship between the fish density and to refers for the acetobin nutrients for the plant, because no need deficiency and need for the plant to be very healthy and an increase of the production in this system. The pumps we are using the same Michelle talking on this that's presentations about the flow rate, and for the pump time is very good, and how the head pressures it is very high or very low, and the energy of the efficiency. This is very have pictures, maybe it's very clear about for the you see about for the irrigation, and we have the return pipe from the fish tank, because I combined between the aquaponics and the RAS systems. This is the valve using for the water return from the fish tank collections after the filtration from the plant bed to return again to the fish pond with the high aerations in the fish in the pond. The optimal waters parameters we and our colleagues, it is to fix between the optimal of the water quality to succeed for the plant and for the fish as possible as. the pH between from the 6.5 until reach 7 or 8. It is between together to optimal for the fish. The temperature is about 20 to 28, but when my records about 28, it is very rich. Reaching that's the dissolved oxygen, it is very good between 6 milligram, but this around of the level. And the ammonia, it is always, alhamdulillah, it is below of the 1 milligrams per liter. And nitrate and nitrate is very important. We should all the times it is fixes in this system. The treatment every day I am measures of the pH, the temperature, is with oxygen every day, but the ammonia I am working that it is every week 2 controls of the ammonia. And about the maintenance and the troubleshooting, all the times we saw about the machines. The machines is working about 24 hours. So we have sometimes a problem because we doing the aquaponics system in the greenhouse. The greenhouse, that's meaning absorb the temperature from the outside to inside. That temperature is very high, and the machines, it is working. That's meaning it is reduce the temperature. Sometimes some of the dust about the vans, it's working all the time. This need all the time for the cleaning and for the putting of the fixing sometimes, and we should. I suggest to putting other bumps or other blowers beside together, because when it is no working one, we working the others directly after that, because this system not need to take time to do it, because it is very risk, and we have intensive of the fish in this system. So we need very directly to doing something for the water. About the trouble, we should know. I am talking about if the van may be not working, we should know that, identify the source. What is the source to doing? Why the van it is not working? It is from have some problems or some burn of some price, or the electricity, it is very high or low, maybe difference from time load or not load. We should pick identify the source to treatment. This is a problem to fixing about this and putting the solution about solving this problem from the procedure. How can do to solve this problem in the future? Because when it is happened, we should thinking about the future. So we advise for all to regular about the inspection, about for everything science, when the system it is for the blowers, for the pipes, or for the timers not working. We should all the times you go to the systems and check everything to know everything about which is have some problems or maybe not working as you want will. The cleaning and lubrications every time, especially for the pumps and the blowers, because I am not using of the bed wheel. I am using about for the blower injection. So we that's meaning it is the same of the pump. We should fixing all the time and cleaning everything about in these machines. I am sorry. And we should put everything for the filters when we have a spare some of the materials is for the vans, or some materials all the times it's which have very have problems all the every day or every month, maybe the vans and some dryers or lubrication. We should do all the times of the oil that's found in your system. A professional service is very important because the engineer for the agriculture, we should know everything about for the system, how it is work. If have a mechanic professional, it's very good. If not, we have laborers working for the mechanism or mechanical to how to fix of these pumps or for these aeration, because it is very important, especially for all the system is depending of the pump and for the blowers to returns of the water and to the increase of the oxygen. Energy efficiency is very important. We know that this system, it is working of the electricity. So when using of the solar energy is very good, but we using the electricity from the company. With that means sometimes we have overload of the electricity, sometimes the low. Maybe this is the burn of the some machines. We should good pumps have good working and very strong. This is very good for you to increase of the these systems to work. The aeration the same for the blowers, because this is very important to transfer of the oxygen, and that's the intensive of the fish intensive systems that will increase density. You don't wait the time, so should working all the time is very quickly and not only to see what you want to do. You should do very quickly and faster to solve this problem. System designs maybe sometimes if you have a writing design for the system, sometimes when you apply in the field, it is not working some pipes or the system is not working very efficient. We should about that to doing something to mistake for this design or for the connect of the pumps between the grow bed or between the fish pond. I think we suggestion about renewable, about the sources for the energy. This is energy very important about that. The cost of analysis is very important because the energy, it is a relationship for the cost, and the system is dependent for the energy. When the energy is very high using and the cost is very high, and the production for the plant and the fish is very high, we should doing and search about the simple technique and have a good efficient for the production, and the same times to reduce the cost all the time to give a maximum profit, because these systems is very high in the cost designs. So we should about the relationships between the cost and producing of these machines. This system we are doing, because I am talking in the first time, it is the research. As a research, because it is follow-up of the center, we doing of the, I think this is the grow bed we are using. It is different size, about to 1 meters to the 4 meters. It is as the replicate we have in this system. We have a small tank IBC. It is a biofilter, because the water from the fish go to the biofilter, and after that we go to the waters, go to the other pipes to supply the grow bed by the water, and after that we are have the siphon belt go to the outside in this system. This is the fish pond. We have the blowers beside, you see, and we have electricity, everything, because I need to the safety for the labors. I don't need to do to have anything, and it is connecting by the safety of the electricity, and the same times it is connected by the pipes in the inside, and submersible in the fish tank. I am using because I was using of the deep irrigation in the system. And after that, we have the return waters from the fish tank, our collection fish tank. That again, because I am comparing between the aquaponics and for the RAS system. The density, we have some the here. This pictures, it is very have the fish is the density is a difference between the fish pond between the fish pond. It is have from I am using from the 60 until reach 150 cubic meter in the cubic meter. And this is the plant I am using. This is a plant. It is have because I have many difference of the density of the fish. I need to study of the relationship between the density and the growth of the plant. Have difference or not difference? I want to see about that. This is the main objective for this research. Thank you very much. Any question? I am ready. Host, share.
Thank you very much. Since there is almost no time left for today's webinar, are there any other questions? Gertrude?
Sorry, just for the last presentation, I saw these little sets hanging down from the tubes into the water of the RAS system. What was it? Or what experiment was it for, Dr. Khraisat?
Okay, we are study the evaluations of the relationship between the density of the fish and for the growth of the plant, because in the Jordan we're using the density in cubic meters about in these the aquaponic systems about the 60 fish per cubic meters. So I want to know about how many fish we can using maximum to give high growth of the plant. We using about starting as the farmers as the control 60 fish per cubic meters, and the treatment second treatment about 90, and the third treatment about 120 for a cubic meter we're talking about, and the fourth it is using about 150 cubic meters for the fish. So I am now it is about 2 months. It is this experiment. I am seeing when the density it is very increased. That's increase. That's meaning I am see high for the growth of the plant. If you enters for the row, we can see the difference. It is very clear. It is not absent. So virtual, we can see this. This is the main, because these systems have the plant deficiency. It's many problems in this system. If you give perfect all requirement for the fish, okay, excuse me, all requirement for the plants, that's meaning the system is very good and very success. And at the same time, the fish is very healthy. This is we can control about it. The fish healthy, the plant is very grow. That means I am in the safe for the experiment.
Thank you very much. So just as last words, maybe I mentioned it already before, but I would like to mention it again. When you talk about the maintenance or any kind of adaptations of the system, there's one good thing that we try to do always in our lab. So Thursdays and Fridays are the days that you say do not touch the system, especially if you would like to have the weekends free.
So any kind of operation or changes on the system, if you have a working day from Monday to Friday, are done between Monday and Wednesday, and Thursday and Friday are just to check if the system is running. Otherwise, I mean, I'm sure that the ones that are working with fish already know this, but if you get a night alarm, and if there is a system problem, normally it comes or on Friday evening or on Sunday morning. So the rule in our lab is do not touch the system on Thursdays or Fridays, but do all the maintenance between Monday and Wednesdays. And if we will have some more time later on in our second part of webinars in autumn semester, I can tell you a few more of funny stories of the maintenance problems and what not to do, especially if you would like to sleep well during the night. So with this, I would like to thank you very much. I would also like to thank you both speakers. And then see you in 14 days when Elisa Apolloni will present her part on simplified hydroponics from University of Bologna. Unfortunately, I will not be able to attend, but Michael, Ranka, and the rest of the team will be present and lead you through the webinar. So from my side, have a great holidays, and I see you with this part 2.
Homework. Thank you.
Homework. Yes, go ahead.
Yes, I think all of you are keen on learning what will be the homework this time. And I have good news for you, because we think that last time the homework was a little bit more extensive than before. We decided that we give you another 2 weeks to fulfill the homework from last week. So we stick with the same RAS design that we had 2 weeks before. All of you that already sent in something are fine then. Probably you would want to improve your design with what you learned today, but all that haven't sent in something until now can do it in the upcoming 2 weeks.
Thank you very much. And then see all of you in 14 days.
Yeah.
Bye-bye.
See you. Bye.
Bye-bye.